RF Man here. Today I'm going to continue my discussion on superheterodyne receivers. This will be part 4 of a 4-part video. I've already discussed in parts 1, 2, and 3 small signal RF amplifiers, frequency mixers, bandpass filters, and frequency dividers. Today the focus is going to be on frequency multipliers. So what is a frequency multiplier? In simple terms, frequency multipliers can multiply any input frequency by a factor of 2 or 3 or 4 or even higher. They're also used in frequency synthesizers. Remember the discussion about dividers? We have a crystal clock oscillator, and we take that oscillator and we divide that frequency up for different purposes in the superheterodyne. Same applies here. You'll find frequency multipliers used in frequency synthesizers and other circuits in a superheterodyne. So let's take a look at what a frequency multiplier is, how it's designed, and we'll demonstrate a few examples. So this is a what they call an odd order, so it's a third order filter. And basically what you do, if let's say you had 10 megahertz and you wanted to make a frequency tripler, okay, so that would be the third harmonic, right? First harmonic is the fundamental, 10 megahertz, second harmonic, 20 megahertz, third harmonic, 30 megahertz, but that would actually be a frequency tripler. So what you do is L1 and C1 are used as input matching circuits for 50 ohms. And then we have a couple of diodes here for rectification. But what really makes this work are the tuned circuits. So you'd have to determine, okay, I need 30 megahertz, right? So you have to determine the resonant frequency of 30 megahertz, selecting a value of L and C. Okay, you would do that for the parallel circuit as well as the series circuit. And then what happens here, remember, parallel circuits have a high impedance at the resonant frequency, and series resonant circuits have a low impedance. So here's the formula for resonance, and there's different versions of this formula, so you can start with a known value of L and calculate the C for any desired frequency, or you can start with a known value of C and calculate the L for a known frequency. So either way, this formula can be rearranged, and there's examples on the internet how to calculate and determine the value of L or C for any given value of F. So if this has a high impedance at 30 megahertz, right, the third harmonic, it's going to block 30 megahertz, but it's going to shunt all other undesired frequencies to ground. And this circuit has a low impedance at resonant frequency, so it's going to pass the 30 megahertz, and it's going to act as a high impedance or an open for all frequencies below the resonance. So that's how this basically works. This one will shunt all frequencies except 30 megahertz, and this one will pass 30 megahertz and block all other frequencies. So that's how these tuned circuits work. Okay, here's another example down here. Basically just two tuned parallel circuits, again using this basic formula and a diode to interface the two. I built this circuit. It works pretty well considering how simple it is. Here's some other examples, more tuned circuits here. More tuned circuits here. This one has a diode bridge, which I am going to demonstrate a version of this, so we'll talk more about that. Here's another frequency tripler that uses a pair of transistors and a tuned circuit. And here's a frequency doubler that uses a single transistor. And yes, another tuned circuit. So here we have 1 megahertz going in. Okay, you tune the resonance for the second harmonic, 2 megahertz, and it becomes a frequency doubler. So here's what we're going to demonstrate first. It's very simple to just take an amplifier, amplify a sine wave, an RF signal, and then use a bandpass filter and select what harmonic you would like to filter out. So in my case, I'm going to use 8 megahertz. I'm going to amplify it and have a bandpass filter for 16 megahertz. So I should get basically 16 megahertz on the output, which would effectively double the frequency. So let's start by taking a look at that one. Let me just shift over so you can take a look at the setup here. This is my function generator I've been using for all the videos. You can see there that it's set up for 8 megahertz. And then if we come down here, you can see the RF amplifier here that has a gain of about 25 dB. And then we can see this is the same 16 megahertz bandpass filter I used in some of the other videos. So let's take a look at the first waveform. So let me exit this. Okay, and then we'll take a look at the waveform itself. Make some quick adjustments here. Change the time base. Okay, and what do we see? Well, we have 8 megahertz going in, like we showed here, and we have 16 megahertz on the output, which is the second harmonic. Now let's take a look at the frequency components. We'll take a look at the FFT, and we'll see what that looks like. So let's move this out of the way here and change the volts per division, change the time base. Okay, and let's look at the cursors. Okay, so X1 is my first cursor here, and you'll see that there's the 16 megahertz. Okay, and then I have 32 megahertz to see if there was any harmonics. But if you take a good close look at this, most of the harmonics except the fundamental are just slightly above the noise floor. So I'm getting a good attenuation of all other harmonics. And this is the fundamental, but I'm about 25 dB below the fundamental. So this simple technique of just amplifying a signal and then selecting what harmonic you want to filter out works pretty well. So this is 8 megahertz in. As you can see, 16 megahertz out. I could have picked the third harmonic, would have been 24 megahertz. By the time you get to the fourth harmonic, it gets a little more challenging because the amount of attenuation by the time you get to the fourth, fifth harmonic may be too low. But clearly this method can be used for either a frequency doubler or frequency triplet. So let's take a look at the other two methods. Give me a moment to set that up. All right, the next circuit that we're going to demonstrate is a circuit from mini circuits. This basically matched 50 ohm impedance on the input and the output. Okay, it has a very wide range. Okay, it's very broad-banded from 20 megahertz to 1 gigahertz. Actually, I tested it down to 10 megahertz, works fine. And this is a passive device. The circuit we saw before could be considered an active device because we had a amplifier with a single transistor in there, so I'd consider that one active, but this one's passive, and the third one I'm going to demonstrate is also passive. So this is what the device looks like. It's an AMK-2-13 Plus. Okay, very easy to use. As I said, already matched to 50 ohms, and you just apply the input and measure the output. So let's take a look here. Let me go back to my PowerPoint slide, and we'll give you an idea of how this one works. Okay, so this is the one we're going to demonstrate now, Mini Circuits AMK-2-13 Plus. Okay, and that's very similar to the analog devices HMC188. Okay, and here's the internal schematic, and these two basically are identical. If you look at this one closely, you'll see it's very similar to the frequency mixer. The only real difference is that the frequency mixer uses a diode ring and the multiplier uses a diode bridge. So this is basically the same as a full wave bridge rectifier used in power supplies. So you can see the configuration there, and still has a matching transformer on the input and the output. It's wired a little differently, but essentially it's very close to a mixer design. Okay, so let's take a look at the circuit first. This is the frequency multiplier. Okay, and I have it set up on a perforated board there, and we're going to be demonstrating that from 10 to 50 megahertz. So let's take a look on the scope. Okay, this is the output waveform. So you can see here I'm at 10 megahertz, and then I'm basically going to go 20, 30, etc., all the way up to 50. So here we are, 10 megahertz. You can see the output there, 20 megahertz. Now 20 megahertz, we can see 40 megahertz. 30 megahertz, we can see 60 megahertz. 40 megahertz is 80. 50 megahertz is 100. Okay, and here's the limitation of my function generator, signal generator, 60 megahertz, and you can see 120, which is actually beyond the bandwidth of the scope. It's only a 100 megahertz scope. So let's back it back down a little bit. Let's say 20 for good measure here, and let's look at the harmonic frequencies. Take a look at the spectrum here. So some quick adjustments, we'll reduce that and change the time base. Okay, get our cursors going here. And yeah, number one cursor. I'll move that over here. And let's get number two just out of the way. I don't confuse anything. Okay, and you can see function generators on 20, and if we look at the spectral analysis, the frequency components here, we see that's at 40. Again, it says 40.6, but that's kind of the resolution of my scope. If I go right to the base there, it's 40.2, and it's going to go to 40. So somewhere in the middle there, 40 megahertz. And you can see 20 megahertz. Okay, I'm going to guess it's that one, but it's just above the noise floor. So let me see where we're at here. Yeah, that's it. That's the fundamental there. Okay, so we got 10, 20, I'd say 30 dB difference. Works quite well. So again, very easy to use. It's already matched, 50 ohms in, 50 ohms out. Okay, so pin 3 is the input, pin 6 is the output. It's that simple. Then you ground the rest of the pins, and there's a no connect on pin 2. It works very nicely. So now, next one we're going to demonstrate is this circuit here, which I built on a breadboard. And again, internally, these are identical. I thought it would be interesting to build and test this circuit. So let me set that up, and we'll demonstrate that as well. All right, so here's the last frequency multiplier I'll be demonstrating. There's two versions of this that I'm familiar with. One uses an input transformer and just the diode bridge without an output transformer. And then one uses an input transformer, the diode bridge, and an output transformer. Now again, this is similar to the mixer circuit, so you can go ahead and wind your own transformers. This is material 43. This particular one is trifle wound, so you just twist 3 wires together and then about 10 turns on the toroid. Okay, and there's another way of winding that I'll show you. That's just a little easier for me. It works fine. The advantage of having the output transformer, when I compared these two circuits, this one provides a lot more attenuation on the fundamental frequency. So I prefer this topology over this topology for just a simple addition of one more transformer. So let's quickly take a look at the circuit. Okay, here's our circuit, and as I said, very similar to the mixer. I'm using the same input transformer and output transformer. Okay, and then here, instead of a diode ring, I have a diode bridge, and this is the mixer that we demonstrated in the last video, so you can see some similarities there. Now this is a breadboard, so this is going to be limited to just the high frequency. I'm going to try to get it up to 30, maybe 40 megahertz. If you build it on a perforated board, you'll find that the performance is much better without all the lead lengths and jumper wires and effects of the breadboard. There's a lot of parasitics there. But I thought for this demonstration, I would just go ahead and breadboard it and see how it performs. So let's take a look at the waveforms on the scope. Okay, and here we are. We are at 10 megahertz right now, as you can see on the function generator here. 10 megahertz, and I'm going to do the same thing. I'm just going to step up the frequencies so you can look at the effect on the scope. Okay, so that's 10, and you can see here we're 20 megahertz, and then we'll go ahead and go to 20, and you see 40, and we'll go up to 30, and probably have to increase the voltage per division. Yep, you can see 60 there, and let's go ahead and try 40. Maybe we need to raise the amplitude a little bit, perhaps, and try to re-trigger on that. No. So yeah, about 30 megahertz is the limitation. It'll go close to 100 megahertz if you put it on a perforated board. Will work at a much higher frequency and respond much better. Let's go ahead. That's back down to 30 megahertz. And we can take a look at the spectral components here. So let's look at the FFT real quick. Again, this is the fast Fourier transformation mode of the scope. It changes the scope from the time domain to the frequency domain. So let's change the volts per division and some adjustments here. Bear with me. And there we are at 40 megahertz here. And this is the fundamental, 20 megahertz. And again, I'm looking at 10, 20, 30, better than 30 dB difference between the two. So excellent performance on this. So that's the demonstration. Just one takeaway from my experience: grounding is extremely important with these type of circuits. So you want to reduce your ground loops and keep your grounding to a minimum. You may even have to experiment to see what are the best grounding points in the circuit. I don't know if there's an exact science behind that, but that's what I have learned from my experience. So I hope this is helpful. RF Man.